Hello everyone, this is me again on Mathematics for Engineering 3. This is the third video on the differential equations. And in the previous video, we talked about the separable differential equations, right? And in this video, we're gonna talk about another type of differential equations. When m and n, the coefficients of dx and dy are homogeneous of the same order, and we're gonna study how to do that in this video. Okay, let's start. Okay, the next topic is the third one, the ODEs, whose m and n are homogeneous functions of the same degree. Okay, in the previous section, we know how to solve the ODEs when it can be written in this form, right? Ax bx plus by dy equals 0, and this is separable, right? We know how to solve the separable differential equation. You just integrate them, right? And just get c here, and that's easy. And that's a special type of ordinary differential equation. And right now we're gonna look at another type, which is called the ODEs, where the m and n are homogeneous functions. So first, you might have a question that what the homogeneous functions are. So this is the definition. A function f is said to be homogeneous of degree n if and only if f of tx, ty equals t to the n f of xy for any t, any positive t, and non-negative integer n. What does it mean? What does it mean? You just need to look at here. F is homogeneous if you put t in here. If you put t with the x and t with the y, right? And then you can pull the t out of the function. So to make it clearer, let's look at some examples. Here, is it homogeneous? Is it homogeneous? So it's the same as to ask if f of tx, ty is t to the n f of xy, whether or not that's true. And if that's true, this function f is homogeneous of order n. Okay, so let's solve it. So f of tx, ty is, what is it? F of xy is xy times log of x plus y divided by x minus y. So f of tx, ty is the same as to substitute x here by tx. So what I have here is tx. See, we basically substitute x here by tx. Make sense? F of xy is xy. F of tx ty is tx and ty. And we substitute y here with ty. Make sense? So it would be log of tx plus ty divided by tx minus ty minus tx squared cos of tx divided by ty. Does it make sense? So we have f of xy, right? So if we want to have f of tx ty, we just basically substitute x by tx and y by ty in here. Okay, so Then we have that is t squared xy log of, here I pull the t out, x plus y. T here is x minus y minus t squared x squared cos of dx divided by t. And it's pretty clear that t's here are cancelled out and the t's here as well. So what we have here is t squared xy log of x plus y divided by x minus y minus t squared x squared cos of x divided by y. And if I pull t squared out, I'll get xy log of x plus y divided by x minus y minus x squared cos of x divided by y. And as you can see, this thing is actually fxy, isn't it? It's exactly the same. It's exactly the same. So we have here that is t squared f of x. So we can conclude that this f xy is a homogeneous function of order 2. Does it make sense? Right? Because we can write f of tx, ty in terms of t squared f of xy. So t squared, it means that the n here is actually 2. Make sense? The n here actually 2. So it's the homogeneous function of order 2. As simple as that. Okay, let's look at another example. Is f homogeneous? So similarly, it's the same as to ask whether or not f of tx, ty is e to the n f of xy. So let's look at f of tx, ty is, right, just to substitute x by tx and y by ty, right? To look at this x by tx and to look at y by ty. So here what we have is tx plus ty sine of ty divided by tx squared. So I'll pull t out, so it's x plus y sine of ty divided by t squared x squared, and it's t x plus y sine of y divided by tx squared. If you look here, this looks almost like fx. This part looks almost like fx, except that you have t here, right? For fx, it needs to be y divided by x squared, not y divided by tx squared. Make sense? So in that case, you can't really, I'll say that we can't write f of tx, ty as tn f of x, y, which means that this f is not homogeneous. Okay? So right now, we know how to, uh, you know, to to verify whether or not function f is homogeneous. So, uh, this is a small trick here. A polynomial with two variables is homogeneous if the sum of the exponents of each term is the same. So if you look here, this is the polynomial, right? The order of here is the exponents here is 5. The sum of the exponents here is 5, and the sum of the exponent here is 5 as well. It's 4 and 1. So if it's 5 5 5, it means that this f is homo. Here the sum of the exponents is 6 6 6 and 5. This means that this function is not homogeneous. The sum of the exponents here is 8, right? 3 and 5. This is 8 as well, and this is 8, which means that this function is homo. Okay, but for these examples A, B, C, you can look at f of tx, ty as well. Will be t to the n f of x. But it is just an easy way to look at the polynomials, whether or not they are homogeneous. Okay, but if they aren't polynomials, we need to use this definition. Make sense? Okay, so now we know what homogeneous functions are, right? So if you see differential equations that the mxy here and the nxy here are homogeneous of the same order. They are homogeneous of the same order. Right now the thing in front of the x can be x and y. It doesn't need to be only x. The thing in front of dy, it can be function of x and y. So it can be both x and y, right? So we can't really use the the techniques from the separable chapter, right? So, but if you can verify that m and n are homogeneous of the same order, so the way to solve it, first you need to verify whether or not, right? You need to check whether or not m and n are homogeneous of the same order, which is the same as to check that m of tx, ty is t to the n m of xy, and n of tx, ty is t to the n, sorry, there's a typo here, is n of xy. Okay, and if you check it and they are homogeneous of the same order, you look at the number. This is a number. The number of terms of m and n. Which one is smaller? Okay, if the number of terms of n is smaller, we let y be vx. But if the number of terms of m is smaller, we let x be vy. Okay, actually here it doesn't really matter. You can always let y be vx, and you can always be able to solve the problem. But it's just a lot, it depends on the problem. It can be a lot harder. Okay, so for now, just stick with what I'm telling you. So you look at the number of terms of n and m. So if n is smaller, you let y be vx. And if m is smaller, you let x be vy. And then you substitute y by vx or x by vy. And then the problem here will become separable. Okay, I'll talk about that later. Why doing this works. I'll talk about that later. But for now, just just believe what I'm saying. Just believe what I'm saying, and then just use it to solve the problem first. Okay, and at the end of this section, I'll tell you why we should let y equals vx or x equals vy and why it becomes separable. But for now, just believe me. So to sum it up, first check whether or not they are homogeneous, right? By checking these conditions. And if they are homogeneous of the same order, you look at the number of terms of n and m. If the number of terms of n is smaller, you let y be vx. If m is smaller, you let x be vy. I know it's a little bit confusing, but if you look at the questions, it will become much more clearer. Okay, so let's look at the problem. Here, find the general solution of this problem. And as you can see here, in front of the x, you have both x and y. And in front of dy, you have, the x. However, this one is not the same as those in the previous section. We can't really, manipulate it so that it becomes x of dx plus y of dy. We can't do that. You can try, but it's not going to work. Okay? So if it's not working, if you can't really move the terms, to make it x dx, y dy, to make it separable, if you can't really do that, you probably need to think of another approach to solve this problem. So the first one you should think of is, the homogeneous functions. So first, we compare this with m of xy dx plus n of xy dy. So we know that m of xy is actually y log y minus log x minus 2, and n of xy is actually 2x. Even if I'm saying that n of xy is a function of x and y, it's okay if you don't have y here. It's still alright. No problem with that. Okay. Okay, next. First, I'll need to do what? Remember? First, I'll need to check whether or not m and n are homogeneous functions of the same order. So let's look at m first. M of tx, ty is what? Ty log of ty minus log of tx minus 2, right? Basically, I substitute x by tx, y by ty in here. And so I'll have here that is, it's log of ty. If you look at log of ty here, log of ab is actually log of a plus log of b, right? Log of a plus log of b. So in that case, it would be log of t plus log of y. And then it minus, similarly, is log of t plus log of x and minus 2. And get is log of t plus log of y minus log t minus log x minus 2. So the log t cancel out, right? Oops, sorry. The log t cancel out. So this is actually the same as this, right? And let me use some other color. This is actually the same as that. Okay? Okay? So we have that this is T m of xy, which means that m is homogeneous of order 1, right? Because it's t to the power of 1. Make sense? Sense? And then we need to do the same for n of tx, dy. But this one is a lot easier because it would be just 2 of tx, right? And that's actually 2 of t of 2x. But 2x is actually n of xy. So here we have that n is homogeneous of order 1. So right now we can confirm that m and n are homogeneous functions of the same order, right? Right? So the first step is done, right? To check, the first step is to check whether or not m and n are homogeneous of the same order. So they really are. So what's the next step? So I'm running out of space, so I'll make this a little smaller. I hope you guys can read it. I'm gonna manage the space here. So next, number 2, I'll need to look how many terms are in m and how many terms are in n, right? So if you look at, term m here, you have got like 1, 2, 3 terms, right? Right? But for n, you have got only 1 term. Make sense? Make sense? So, I just said that we look at the number of terms of m and n. So if the number of term of n is smaller, we let y be vx. And in this case, the number of term of n is much smaller, see? So we let y be vx. Does it make sense? So if we let y be vx, so we have that dy is actually v dx plus x dv, right? That's the formula from calculus 1, the differential, right? The derivative of fg is f dg plus g df. Make sense? So dy is v dx plus x dv. It depends on how you memorize it. Somebody use front d back plus back d front. It's up to you, okay? Or f dg plus g df. Up to you. Okay, so I'll substitute this back into this equation. So what I have here is, so y is vx, right? This is the y is vx. in it. Log of Vx minus log x minus 2 dx plus 2x dy is v dx plus x dv equals 0. Does it make sense? Okay. Then what we have here is Vx. This is log of V plus log of x minus log x minus 2 dx plus 2x v dx plus x dv equals 0. And this is cancelled out, as you can see. So what we have here is Vx log V dx minus 2Vx dx plus 2xv dx plus 2x squared dv equals 0. And you can see that these are cancelled out. Okay, so what you have is Vx log V dx plus 2x squared dv equals 0. And I told you that after we do the substitution, this ODE becomes separable. So it doesn't look separable now, but you need to somehow make it look separable. Okay, so we can do that by I'll divide the whole equation by x, so I get v log v dx plus 2x dy. Sorry, I'll just divide everything by x squared. So this is what I get. I did that to remove x squared here, so that in front of dy we won't have x squared. Make sense? And if I put x squared here, this 1 cancel out and we still have 1 left here. And then I divide the whole equation by 1 over v log v. So this is what I have. And as you can see, the coefficient of the x has no v, and the coefficient of v has no x. So this becomes separable. In x and v. So guys, when you check and you know that m and n are homogeneous of the same order, and you do this substitution, it's 100% that after you all do all this substitution, you need to get separable differential equation. If you don't get the separable differential equation, it means that you did something wrong, in somewhere. I don't know, but you definitely did something wrong. Okay, so guys, before I proceed, just to sum it up, you see the function here, the differential equation here, the ODE, and you can see that you can't make it separable, right? You can try, but it won't work. Then you check whether the m and the n, this is m, this is n, are homogeneous of the same order. And if they are, right, if they are homogeneous of the same order, you just do some substitution. You look at the terms of m and n. Here n has one term, but m has three terms. So if n has, smaller number of terms, you substitute y by vx. So dy is v dx plus x dv, and then you substitute this into the problem. So you do the math, and then at the end you need to get the separable differential equation, and then we are back to the previous section. Okay, however, I'm not gonna leave you here. Okay, good news, I'm not gonna leave you here. I'm gonna solve this as well. Okay, so let me go to the next page and look at this. So how to solve this differential equation? So it's back to the previous section, right? So you just need to integrate x dx plus integrate to v log v dx equals c, right? So the integrate of the integration of 1 over x is simple, is log of absolute x. So right now we're looking at the integration of v log v d this is dv, dv dv, and to do that we can do substitution. I let u be log of v, so du is 1 over v dv. Okay, so here I'll have that this is the integration of 2 divided by, if you look here, log of v, right? But log of v is actually u, so it's u here. Make sense? It's actually u here. And you also have that v 1 over v dv is actually du, so I have du here. Make sense? And this is, the integration of this is just to log of absolute u, which is to log of 1 over v. Oh, sorry. Log of. Right? One is log of log. Does it make sense? And then I just plug in what I have, computed. So I plug in here. So the integration of 1 over x dx is log of absolute x, and the integration of u divided by v log v is 2 log of absolute of log of absolute v. Okay, oh sorry, you can put absolute in there, doesn't really matter. Okay, equals c. This is log of x plus log of log of v squared c. Make sense? Right? You can push 2 here, up here. And what you have is, the log of absolute x, the log of v squared equals c. But I can get rid of the absolute here because you have squared here. So if you square it, is always positive. So I can get rid of the absolute. And then I push the log up there. I'll have that absolute x log of v squared is actually e to the c. Guys, e is a constant, right? And c is another constant. So as I told you, we can call this c star, right? Another constant. And here, we have the absolute here. I told you before that if we have absolute of something equals constant, we can just get rid of the absolute, right? Right? But you may think that there's no absolute here. But guys, this is always positive, right? This is always positive, right? This is squared, right? So it's always positive. So if I have 5 and I put absolute in there, is it the same thing? It's the same thing, isn't it? Right? Or if I have, I don't know, 10 and I put absolute, as long as the value is positive, I can just put the absolute in here, right? And in that case, I have that is absolute of x log v squared equals c star. Make sense? Because log v squared is always positive, so I can put the absolute on it. And right now we have some absolute of something equals constant, so I can take the absolute out. So this is the solution. Let's call it c double star. So the last step is to substitute v back into the solution, because before this we let y be vx, right? So v is actually y divided by x, so we need to substitute this v by y divided by x, because it's the solution of this problem, right? And this problem is, it has x and y, not v. So to answer this question, we need to to get rid of v. So to do so, we have that is x log of y divided by x squared equals c star. That's it. That's it. Okay. So it's as simple as that. First, right, let me recap. First, you get the m and the n here. And you see that, they are not separable. So you somehow check whether or not they are homogeneous functions with the same, the same order. And if they are, you can do substitution, right? You first look at the term here, n and m, to see which one has smaller terms. Like m here, it has just one term, right? But m, it has like 3 terms. So in that case, we will let y be vx, and then we do the substitution. And after that, we will end up with separable differential equation. And then we solve it as in the previous section. Make sense? And in the end, we need to substitute, you need to get rid of v by, substituting v by y divided by x. And that's it. That's the end of the story. Okay? I told you that to let y equals vx or to let x equals vy, both work fine. You don't need to really care about this. You can just, stick with one of them and always do this substitution. But it can be a lot harder. For example, the the same problem. If you notice, this is the same problem as before. We already verified, right, that m and n are um, homogeneous functions of the same order, right? So here, before this, we let y be bx because the number of n x y is smaller, right? Right? But if you really want, you can let x be vy as well, and it works fine. You will get the same solution. It's just gonna be harder. Why? Because if you look here, if you let x be, let me use some other color, x be vy, so the x is actually what, v dy plus y dv, and then you need to substitute this in that. So if you want to do that, you need to substitute this, the x here in here. And that is a lot harder. Why? Because if you look here, you get y log y minus log x. Sorry, log of x would be log of by minus 2, and dx would be v dy plus y dv plus 2x dy. And see, and if you do substitution this way, to let x equals vy, you need to do this multiplication, and it's not fun. See, right? You need to multiply this, and it's really not fun. That's why I told you that if you want to do the substitution, if the terms here is 1 or 2 terms, they are smaller, they have less terms, so you substitute dy so that you don't need to multiply the big expressions. Does it make sense? Right? If you look at the previous example, we substitute dy, right, and we put dy here, and it's as simple as that, right? Just multiply that. But if we instead begin with this, we get this dx, and we need to substitute it here, and we are left with this, and we need to do this multiplication, and it's a lot harder. Okay, but if you want to do it, you can do it, and with some works, you're gonna end up with separable ODE. It works exactly the same. So you can use y equals vx or x equals vy, your choice. But I would recommend you, if the number of terms here is smaller, just use y equals vx so that the dy is small when you do the multiplication. But if the number of terms here is smaller, you use x equals vy. Okay? We'll look at more examples, and it will be more clearer. It will be clearer. My back hurts now. Today I've been recording the videos for, I think this is the 6th hour. It's really terrible. I used to be really fat. If I should show you the picture. I'll show you later. I used to be like 114 kilograms. It's like this big, and it's horrible. That was when I was doing a bachelor at your age. Uh is the terrible thing about being fat at Kasetsart University. You know, food is was pretty good there, but the terrible thing was that you have the chairs, right, in the you know in the lecturing rooms, and you have the thing that you put it here so that you can write on it, right? But I was so fat so that I couldn't put it on because it got stuck on my belly. That was horrible. Lots of people have asked me how I lost weight. Because right now I'm like half of what I was, and my peak was, as I told you, 114. At the beginning I went for the horse riding, to ride a horse, and it's terrific. It was terrific because within 2 weeks the weight um, has reduced by, I think, 2 kilograms. But I stopped after that because it's 2 kilograms from the horse. Come on, guys, it's for 114 kilogram boy sitting on a horse. That's not good for animal. Okay, my weight remained the same. Okay, let's continue. Here is pretty much the same as the previous one, right? Uh, we have mxt here and nxt here, and as you can see, uh, you know, you might tell me that okay, just factorize this. The one that we did before, just factorize this, and maybe we got lucky, and they become separable. I don't know, maybe they do, but I don't think they would. Okay, you can try, but I bet they won't become separable. Okay, so if you try to make it separable and it can't be separable, we need to look at what homogeneous functions. So the m of x y is 4x squared plus 7xy plus 2y squared. So this is polynomial, right? It's polynomial, and you can see that the sum of the equation here is 2. The sum of the the sum of the exponents here is 2. The sum of the exponents here is 2 as well, and here is 2 as well. So the sum of the exponents of all terms are equal. So it means that this is homogeneous function of order 2. You can go the same way, m of tx ty equals t to the n m of xy. You can do that, but I'm not gonna do it, right? Because it's polynomials. We know the faster way to do it. Why bother going slowly? Similarly, for the n of xy is minus x squared, and it's polynomial, right? And the sum of the exponent is 2, and there's only one term. It means that it's the same, right? It's the same. So it means that it's homogeneous as well of order 2. So we have done the first step, which is to check, right? Next, we need to look at the number of terms, right, in front of dx and in front of dy. So here, the number of term of n is smaller, right? So I'll let y be Vx. Does it make sense? I'll let y be Vx. And same, dy would be v dx plus x dv. Right? And then we do substitution. Sense? Okay, to do the substitution, we have what? 4x squared plus 7x, y is vx, plus 2 of vx squared dx minus x squared of v dx plus x dv equals 0. Make sense? Just, substitute y equals vx and dy equals v dx plus x dy in this equation. Okay, and then what we have is it's going to be 4x squared plus 7x squared v plus 2x squared v squared dx minus x squared v dx minus x cubed dv equals 0. Okay, so we have that is 4x squared plus 7x squared v plus 2x squared v squared minus x squared v dx. So I just push this term in there, okay, because they both have the x. Okay, and then we minus x cubed dv equals 0. After that, I'll just rearranging the terms. I have got this plus this and this are the same expression, right? So I have 6x squared v plus 2x squared v squared dx minus x cubed dv equals 0. Make sense? And can I pull 2x squared out? So they would be 2 plus what is it, 3v plus 2v squared dx minus x cubed dv equals 0. Does it make sense? Does it make sense? It's a lot of calculations, okay? So you need to be very careful with it. But you know that at the end you need to end up with separable differential equation. Okay, so I divided everything by x cubed and 2 plus 3v plus 2v squared. So I will have this 2 over x dx minus 1 divided by 2v 2 plus 3v plus 2v squared. Oops, sorry here. I pull 2x squared out, so here there's no 2 anymore. Sorry, no 2 here anymore. So it'll be just that dv equals 0. Okay, so right now it becomes separable. Make sense? So the only problem is to solve this separable ODE, and I'm going to solve that for you. So to solve this separable ODE, we just need to integrate, right? Right, and this will become C. So this is easy. You know, the integration of 2 divided by x dx is just 2 log absolute x. That's it, right? The other one is harder. The other one is harder. Do you remember how to integrate this function? See, you know, after all the computation, it goes down to calculus 1. It goes down to how to integrate, you know, the functions. So this one, do you remember how to do that? Let me do it another one more step. So here I factorize it. It'll be v and 2 and 1 plus and plus ev. So does it look familiar? How to integrate this function? That's it. You need to use what we call partial fractions. Partial fraction. So what it is, first we need to write this v plus 1, v plus 2 as a divided by v plus 1 plus b divided by plus 2. So I think, you know, many of you already recognize this. So and after that, we multiplied the whole equality by v plus 1 times v plus 2. So we have that is 1 equals a v plus 2 plus b plus 1. And then if we let v be minus 2, we have that is 1 equals 0 minus b, which means that b is actually minus 1. And similarly, if we let v be minus 1, we have that is 1 equals a, which means that a is 1 and b is minus 1. So in that case, we have that 1 over v plus 1 and v plus 2 is 1 divided by v plus 1 minus 1 divided by v plus 2. So the integration of this dv is the integration of this, which is the integration of this. And that is log of v plus 1 minus log of v plus 2. Is it hard? Is it hard? Okay. So we substitute this and this into this. So we have that is 2 log of absolute x minus log of v plus 1 minus log of v plus 2 equals c, which means that is 2 log of absolute x minus log of v plus 1 plus log of v plus 2 equals c. Sorry. Okay. I'll push the 2 here up here. So I'll have that is actually x squared times v plus 2 divided by v plus 1 equals e to the c. Right? Right? And we can call this c star. It's the same thing, it's a similar approach. Okay. And then we need to substitute v by what is it? Y is vx, right? So v is actually y divided by x. So we need to substitute that back into the solution. So what we have here, because v is y is vx, so v is y divided by x. So what we have is x squared y divided by x plus 2 and y over x plus 1. Right? But if you want, you can multiply x here and x here, you know, to make these two terms to have the same denominator. And in that case, we have that is x squared 2x y plus 2x divided by x divided by x plus y divided by x equals c star. And then we have that is x y plus 2x times x divided by x plus y. If you remember, it's a fraction, right? So you can put it here up here, right? You flip between the numerator and the denominator. You flip it and then you multiply it back, and you get c star here. So you get x squared y plus 2x divided by x plus equals c, and that is the solution. Make sense? Okay. Okay, let's look at this problem. Find the general solution of 1 plus 2e to the x divided by y, dx plus 2e to the x divided by y times 1 minus x divided by y dy equals 0. Okay, well, I'll let m of xt be, m of xy be 1 plus 2e to the x over y. So we can see that m of xt tx ty is 1 plus 2e to the x divided by ty, right? And that is actually 1 plus 2e x e to the x divided by y, right? This t cancel out. So in that case, this is actually just m of xy. So is homogeneous of order 0. Make sense? It's homogeneous of order 0. Why? Because here you have t to the 0, right? T to the power of 0. So it's actually homogeneous. So right now we need to look at the other one, the nxt. So I'll let nxt be 2, 1 minus. And similarly, if you look at, sorry, it's nxy. If you look at n of tx, ty, actually 2 e to the tx divided by ty, ty, 1 minus x tx divided by ty, and the t cancel out. So what we have here is 2 e to the x divided by y, 1 minus x divided by y, which is actually n of xt. So it's also homogeneous of order 0. Does it make sense? So then we can look at both terms. Here we have two terms, the mt, the mxy, and here we have two terms as well. So it doesn't really matter if you're gonna substitute x equals vy or y equals vx. So as an example, I will let, because I've done y equals vx for 2 equations, right? For this one, I'll do x equals vy, and in that case, we have the x is actually v dy plus y dv, and I'll do some, I'll do the substitution. So here I get 1 plus 2 e to the vy divided by y dx. Sorry, dx is actually v dy plus y dv plus 2 e to the vy divided by y, 1 minus vy divided by y dy equals 0. So the y cancel out. So what we have here is sorry, I should have had the parentheses here. So I have 1 plus 2 e to the v dy plus y dv plus 2 e to the v of 1 minus vy equals 0. And then we have that 1 plus 2 e to the v multiplied by v plus 2 e to the v 1 minus v, this is dy. So I basically group these two terms together, the terms with y dy, and the other term is plus 1 plus 2 e to the v y dv equals 0. Okay, and here to make it look simpler, is y is actually v plus 2v e to the v plus 2 e to the v minus 2v e to the v dy plus 1 plus 2 e to the, I'll plus it here, plus 1 plus 2 e to the v y d v, and these are cancel out. Okay, so we have the v plus 2e to the v dy plus 1 plus 2e to the v y dv, and we just rearrange the terms, so we get 1 over y dy. Okay, I divided, this is equal 0 though, so I divided everything by y, so this cancel out, so we have 1 over y here, and then I divide everything by v plus 2e to the v. So right now we end up with the separable differential equations. Make sense? Oops, sorry, I've got 2 here, so it should be 2 here as well. My bad. So in the same, in front of dy there are only y, and in front of dv there are only v. So we can solve this by just integrate throughout the equation. So I'll just put it in another page. So how can I integrate this function? I'll look at this one first. Okay, I'll integrate this. I'll look at the integration of 1 over y dy first, and this is log of absolute y. That's clear, that's simple. And the other one, integration of 1 plus 2e to the v plus 2e to the v dv. This looks hard, but it's actually very simple. Why? Because if you let u be v plus 2e to the v, so du is actually what? Dv plus 2e to the v dv, or it's actually 1 plus 2e to the v dv, right? So here we have that is the integration of you can see here 1 plus 2e to the v dv, that's actually du, and here red one here is actually u, right? So we have log of absolute u, which is log of v plus 2e to the v. Make sense? And then we plug in these integrations, so we have that is log of absolute y plus log of v plus 2e to the v equals c. And as I told you, it's actually done here, but to rearrange the term to a little bit more, so we have it here. Try to do it. It's pretty easy actually. V plus 2e to the v, right? Log of this plus this, so it's a log of this times this, equals c. And then you push it up there, so you get this, and you call it c star. or you can just call it C if you want. Just call it C. Another constant. And as I told you like many times, that you can just drop the absolute signs, and this is a solution. This is a solution. Oh, I forgot one thing. You need to substitute v back to the, to to the problem, to the solution. So v is actually what? X is vy. X is v divided by y. Oh, sorry, vy. So v is actually x divided by y. So in that case, it's y x divided by y plus 2e to the x divided by y equals c. Or it can be written as xy plus 2ye to the xy divided by y equals c. Sorry, this actually cancel out. That's x. My bad. Okay, and that's it. Okay, one important question that I haven't answered yet is that why it works, right? Don't forget, we begin with the homogeneous functions, right? And we did some substitution, and then it becomes separable. But why? Right? I just told you that it would become separable, and it actually does, as you can see in the previous examples. But why? But how come? So we're gonna investigate it here. So first, I consider the problem. This differential equation mxy dx plus nxy dy. So I assume that m and n are homogeneous of degree n, right? So I assume this, that they are homogeneous of degree n. So I need to somehow show that if I do the substitution that I told you, this problem needs to become separable differential equation. Okay, so if m and n are homogeneous of degree n, this is what we get, right, from the definition. Okay, and don't forget, guys, t can be any positive value, right? So here, how about if I let t be 1 over x? What do I get here? I would get m of what? 1 over x, so it will be m of 1 is y over x equals 1 over x to the n m of xy. And similarly here, I'll get n of 1 y over x equals 1 over x to the n of xy. So I get these two conditions, right? And then as you can see, if I'll have that m of xy is actually m of 1 y over x 1 over x to the minus n. Get it? Just move this to that side, right? And if this is 1 over x to the n, if I move it to that side, it will be 1 over x to the minus n. Sense? Or, if it's too confusing, I can just write it like this, divided by 1 over x to the n, right? it multiplied m, so then it changed it here. It would be m1 y over x divided by 1 over x to the n. Make sense? And similarly, we have that n of xy is actually m of 1 y, sorry, n of 1 y over x divided by 1 over x to the n. And then I substitute this mn in here. So what I have is m of 1 y over x divided by 1 over x to the n dx plus n of 1 y over x divided by 1 over n to the x dy equals 0, right? But these are the same, right? So I can multiply the whole equation by 1 over x to the n. So these would disappear. Thanks. Okay. So if I divide the whole equation by n1 y over x, this is what I get. M of 1 plus, sorry, y over x divided by n of 1 y over x dx plus dy equals 0. Okay, and I call this term gy. Oh, sorry, g of y divided by x. Just, for convenience, to make it easier to write. So what I have right now is g y over x of times dx dy equals 0. And then what's next? I let y be vx, right? This is what we do, the substitution, right? So dy is actually v dx plus x dv. And if y is vx, so we have that y over x is actually v, right? So this equation becomes g of v dx plus v dx plus x dv equals 0. Then I'll copy this and go to the next page. And after that, we just rearrange the term. It will be v plus dv dx plus x dv equals 0. And then I divided everything by x and v plus gv. This is what I get. 1 over x dx plus 1 over v plus gv d is dv. And now it becomes, as you can see, separable, right? The coefficients of dx, the things in front of dx, is only x, and things in front of the v are only v. Make sense? So it becomes separable. So it's not coincidence, okay? It can be proved in this way, right? So just to conclude the proof, we just let any differential equation that the m and n are homogeneous of degree n, and then we show that if we do this substitution, right, this is just rearranging this equation, right, and then we substitute y by vx, and then we have that the equation becomes separable, and this is why it works. Okay guys, we're finally done. Okay, so just to sum it up, today we studied the the special type of differential equations when the m and n are homogeneous of the same order, right? So at first we talk about what homogeneous is, right? So it's f of tx ty equals t to the n of f of xy, and that's the f is called homogeneous of order n, right? And then if m and n are homogeneous of the same order, we look at the terms, right? We look at the terms of the m and the terms of the n. If the terms of the n is smaller, we substitute y by vx, and if the term of the m is smaller, we substitute x by vy, and by doing so we end up with separable equations, right? And in that case we can just integrate throughout the equation, and at the end we need to get rid of v, right? We need to get rid of v to get the solution in terms of x and y, and that's it. Okay, next time we're gonna look at another special type of differential equations when the m and n are not homogeneous, okay, and of course the equations are not separable, but the m and n are linear equations. So if m and n are linear equations and they are not homogeneous, what can we do about that? How can we solve that problems? Okay, see you in the next video. So enjoy your weekend. Bye bye.